Okay, today we'll be starting with chapter 8. We'll be looking at some special points and then some further cautions. The special point we are going to look at is we are going to look at what is an outlier, a high leverage point, and also an influential point. Those are the special points we are going to look at. So it is very important that you understand them. So we already know what an outlier is because we've been dealing with it way back from when we started doing those box plot and stuffs. So usually when you encounter an outlier, it is first and foremost you should be able to determine that this is an outlier because most of the time you'd see it is we look at the Y plane and you see it's very far from the rest of the observations. And so, whenever you encounter an outlier, it is very important that you figure out why and also fit two models. One model with the outlier and then the other one without the outlier. And so, in doing so, I want us to look at this example. I picked this example from the textbook. Um, so it's a lot, but my focus is for us to focus on the votes between Pat Bachman and then Ralph Nader. So let's go to Start Crunch and then load this data set, election 2000. So I have my Start Crunch open here. And so I go to data and then load from shared data set. And then let me put election. So there you go. This is this is the data set. So we load it and then you can see these are various counties in Florida. And then the votes between Bachman and Nader. And so let's try to um, construct the scatter plot. So let's see. This is stats, and then we go to regression, and then we go to simple linear. So we are told that here the response is the Bachman vote. So let's try to do that. And then the X variable, the explanatory is the Nader. And then let's do that. And then let's hit compute. I'll provide the attendance password when we are done with class. So let's look at the scatter plot. So this is the scatter plot. You see, these are the X variables, but look at the Y here. You see, this is very far from, even though it's within the X ranges, but in the Y plane, it is very far from the rest of them. So this here is an outlier. It is very important that you know, because we'll be talking about high leverage point, and there is a distinction between a high leverage point and an outlier. So for an outlier, first and foremost, you should be focusing on the Y plane. The outlier, focus on the Y plane. You see it is very far. Look at the X. Look at the X here. It is within the X, but then with the Y, it is very far from the rest of them. The other thing too you could also do is to also look at the regression because usually outliers have um, big errors. So for example, we could also look at the residual plot. You see, so let's get here. So we see this guy here. So this is an outlier. So now it is very important that you're able to identify an outlier. Okay, now that we've seen the outlier, now let's look at something here. So let's look at the regression. So you can see, and then this is the coefficient of the explanatory variable. It is 0.14471. You can see from here, or the slope. So this is the intercept, and this is the slope. And then now let's look at R. You see R is 0.65 and R squared is what? 0.427 or 42.78%. This is like 65.40%. Okay, so now that we have this outlier, let's try to identify the outlier. When you click on this, it takes you to the outlier. And so this is the outlier here. So, like I did say, anytime you encounter an outlier, you should figure out why and consider fitting two models. So this is model one with the outlier, and then let's fit another model without the outlier. So let's try to remove this outlier. So I'll do delete row. Okay. And then let's fit again and see. So you see, now we do not have an outlier. Do you see? And then you can see without the outlier, you can see the R squared has increased significantly. The correlation R has also increased significantly. You can also see that the slope has changed a lot. So you can also see these things. So this is anytime you encounter an outlier, figure out why and consider fitting two models, one with it, the other one without the outlier. The other thing we want to look at is so this is what identified outlier fit the model with the outlier included, and then the one with the outlier excluded, and then you summarize observations. So here the observations I could summarize is that we can see R squared has increased from I think it was around 42 point something, now it's 82 point something. There's around 60 something, and now it's 90 point something. So those are some of the things. You could also comment on also the slope, if the slope changed significantly. So those are some of the things you could talk about. So anytime you encounter an outlier, make sure that what you fit two model. That is the recommendation. The other thing we want to talk about is high leverage point. Now, it is tempting to confuse a high leverage point with an outlier. And so I decided to provide a graph to be able to distinguish between the two. A high leverage point is a data point. It's unusual if it's X value. So with the high leverage point, we are looking at the what? The X plane. And then it's far from the mean of the X values. So they are extreme in the X space, but may still follow the overall pattern of the data. Now, let's try to look at what I am trying to point out here. So let's look at these two graphs here, okay? This two graph here is to be able to help you understand what a high leverage point is and also what an outlier is. The first one on the left is the one in green here is a high leverage point. Why is it a high leverage point? Now you can look at the X plane here. You can see most of them are here, but this is 10. It is far from that. It's like 15. You see, it is far from that. So, but then you realize that when you extend the line, it won't be far from the line of best fit if I decide to extend this line. But it is far in the what? In the X direction. You see, it is far in the X direction, but it aligns with the trend. So that is a high leverage point. Now let's look at an outlier. You see the outlier, look at the X. It is within the X, but with the what? Y plane, it is far from the rest of them. So usually an outlier, you should be looking at the Y plane. And then for the high leverage point, you should be looking at the X plane. So for example, when you look at this outlier like this, look at the observations here. See 4, 6, 8, 10. It is this X is within, but the observed, which is the response, it is far from them. So you see that its error is also far from the line. So its error is going to be what? Big. But here, though you can see from this line that it is far from the X values, but it's fitting the overall pattern. Even if you draw the line, it won't be that far from the line of best fit. So you see that's going to have a small error. Remember, the error is what? Observed minus predicted. So this is a graph to be able to show you or explain what a high leverage point is and what an outlier is. Do you have any questions? So usually outliers has large residuals because remember residual is what? Observed, and then the predicted will be somewhere here. It's going to be very large, like we saw in the other example. The other thing we want to look at is influential point. So an influential point is a data point. If we omit from the analysis, it changes the model enough to make a meaningful difference. So for example, you see that the slope will change a lot. And we saw that in the example with the NADA, the voting case, we saw that that outlier point is influential. So anytime you're asked to determine if a point is influential, you should be focusing on whether it's changing the slope here. The value of the slope here is going to change significantly. And sometimes to the R squared, but your main focus should be on the slope. So these are the 3 points we want to talk about. One is the outlier, two is the high leverage point, and three, the influential point. Now let's look at this. We can see from here that this X here is not that influential because I don't think it's going to change the slope that much. But this can change the slope significantly. So this is an influential point. So it's something you should be able to uh, see, and then also whenever you encounter questions on them, you should be able to answer. And then the other thing we would be talking about is that you should always be careful anytime you have influential or outlier point present. You should what? Consider running two regressions and reporting both. You should also be looking out for residual plots or patterns. And then whenever we do summary statistics, because it's a summary of the whole data, they are less variable than the original data. So you should always maintain some skepticism. The other thing I want us to do is to try some problems in your chapter 8 homework. So let's start with question 1. So for question 1, it says that a concert production company examines its record. And then the manager made the following scatter plot. The company places concerts in 2 venues, a smaller one as or more intimate theater, which is plotted in the blue circles, and then a larger auditorium style venue, which is in the what red. So let's see. So we can see the blue here. So this is the scatter plot. We can see this is the total revenue. We can also see that this is the what? The talent cost. And so we can also see we are told that what the smaller auditorium is in blue circles and then the larger auditorium is in red. Now we are being told to describe the relationship between talent cost and total revenue. So, and then we've been given direction, form, strength, outliers. So now, when we have this one here, so when you look at this here, what is the direction? Can anybody help us? What is the direction?
Positive.
Positive. What is the strength?
Moderate.
Okay. What do you see outliers? What is the form? So we can see a line. Do you see outliers?
No.
Okay, I see one here. So usually you guys have answered all of them. So what I always recommend is that now you are being faced with multiple choice. Let's try to eliminate them. You guys said that the direction is positive. So we can see this is negative. So this D is out in negative. So A and D are out. Is that okay? Good. So now we are left with between B and then C. So B is saying that strong positive, and then this is saying weak linear positive. So usually when we did say that if we want to look at the strength, let's try to draw a circle around this point. If the circle is more enclosed, it is strong. If it's wide open, then it is a weak relationship. So the other thing you could also see, there's a difference between the two here. Aside the weak and then the strong, this says there are no outliers, but this says there is one outlier, and then you can see that from here. Look at the Y. You see this is what? Up to 120,000. I think the max and that is like 160,000. You can see from here. Like I've told you already, when you're looking at outliers, you should be focusing on the what? The Y plane. So you can see this is an outlier. So then that takes us to B. If the strength is not really clear for you to see. Does that make sense? Because you are being faced with multiple choice, you have to answer the one that best fits the situation. Does that make sense? Let's go and look at the other one. How are the results for the two venues similar? So this is what the question is saying. How are the results for the two venues similar? So you have to be able to read the multiple choice you have here. We are told that, so there's an increase, decrease, and then, so when you look at this one here, what can you see? We can see that because this is what positive, you can see that when there is what an increase in talent cost, there is also, it also shows what an increase in what revenue. You can, because you already said that the direction is what positive. So you can see B is out. We've also been told that relationship does not mean causation. So these ones are out. Does that make sense? And then the other question is that how are they different? Now, what do they mean by that? So for me, I'll look at this. Okay, they are talking about variability. So when you look at the blue one, the blue ones are more enclosed than the red ones. You can see the blue ones are more enclosed than the red ones. So the more enclosed means there is a lower variability. The one that is not really enclosed or a larger circle means there is a greater variability. So we can see the larger venue has a greater variability, which is true because the larger venue is in red, and you can see because the circle is not that, it's a bigger circle than this one. So this is true. And then revenue for that is easier to predict. If the variability is big, it is not easy to predict because it means that there is what much variability. It means that it is not consistent. The smaller venue has a greater variability, which is not true because the smaller ones is enclosed. You see, they are closer. The smaller venue has a greater variability, that is out. The larger venue has a greater variability, which is true. And the revenue is more difficult to predict, which is true because if the variability is what is big, it is difficult to predict. Any questions on question one?
I have a question.
Good,
Um, for part A, can you explain why that 1 point is an outlier and not a high leverage point?
good. So like I did say that an outlier, we should be focusing on the y plane. Okay. Now let's look at this data set here, or even, okay, even this one here. This is an outlier because I'm looking at the y plane. It is far from, look at the y's here. You see, the maximum is around this side. You see, but look at this one here. Do you see? Look at the horizontal difference. Do you see that? So that is the y. The other thing you could also do is, let's look at this one here. And then you see, this one is very clear because it's really far. You see, from the rest of them, this one is the next, I think this is the next highest one here. So outliers, we are looking at the y. Now let's get to the example one here. So you see the maximum here. Look at the y. It's even less than 120,000. But look at this one here. It is around 160,000. Is that okay? Can you see that?
Yes.
Good. So that is why it is an outlier. And then also the fact that it's not every outlier, it's not all, there are mild outliers. For example, this one here is not a mild outlier. This is a strong outlier. The one we just did too is a strong outlier, but this might not be significant as this one's. And then we said that for a high leverage point, there should be, we are looking at the X plane. Now look at this one here. This is around 75. I think this should be around maybe 80 something. You see. Remember, each point is what X and then Y. Is that okay? So I'm looking at it from, I look at this one here. So I look at it from here. It's a bit far, but not too far. That is why I consider that to be an outlier. Does that answer your question?
Yes, thank you.
Good. Let's get to question 2. Okay, question 2. It says that an analyst tried fitting a regression line to each segment of the data separately to test a model of the whole data and found the plot given below. Let's look at the plot. This is the plot. The model being tested is given by, so January is equal to, this is the constant, and then times December. Okay. Now let's read. What does this say about the analyst's concern about the model? Now, were they justified? Let's understand this. Were they justified in worrying that the overall model might not accurately summarize the relationship? So what is the point? They are worried that the overall model, which is this one here, okay? The overall model is the one we've been given, 612.07 plus point. So that's the overall model. So they are worried that this overall model might not accurately summarize the relationship. Now let's look at the possible answers. So when we look at this one here, the first one says yes, each segment has a different, so you can see here, the line of best fit is different. You can see here is what positive, here is what the direction is negative. This looks like neutral. So you can see. So yes, they were worried. It's true that this might not be able to summarize the relationship because you can see it has a different best line, best fit line, and also different relationships because this is what positive, this is negative, this is also positive. So that is true. So let's look at the other ones. So this one says that yes, they are also worried, and each also has different best line, best fit line, which is also true. So they follow similar relationships. No, the relationships here are not similar. They are different. This is positive, this is negative, and you could see that this was also positive. So that means B is out. No. So here is saying that, and it means that this could be able to summarize the overall relationship, which is not true because we have different line of best fits and also different relationships. Any question on 2? You might not get the same thing as I have, so it's very important that you understand how to analyze them. Any questions? Any questions? Okay, let's look at this one here. We are told that a regression of total revenue on ticket determined by a concert production company is given below. Complete part A and B. So we are given this. Now, it's saying the management is considering adding a stadium style venue that would seat 10,000. What does this model predict? What does this model predict that the revenue if the new venue were to sell out? So then for you to be able to get that, you plug in this one here. So now the question is, so if 10,000, you put 10,000 here and then you do that. Now the question is that why would it be unwise to assume that this model accurately predicts the revenue for this situation? Let's look at the data. So when we look at the data here, the ticket sale, the maximum is at, I would say the maximum is around maybe 3,500. This is the X values here. You can see this is the biggest X here. So let's say maybe 3,500. But this wants to predict 10,000. Remember, we learned that what our model should be able to predict within our X values. That is what we learned, that we should be careful about extrapolation. So you can see this is 10,000. This is far from even our data set. Is that okay? And so now let's look at the possible answers. The model does not account for the cost of construction firm, we are not interested in that. Ticket will not sell, no. The model does not account for the price of the tickets, no. So you see, extrapolation, because we are trying to predict 10,000, but the data set we use, let's say the maximum is around 3,500. Does that make sense? So an extrapolation from the data is unreliable because our data set here ends at what you can see, it ends at what 3,500, but you are predicting 10,000. So remember, I think in chapter 7, we learned that we should be careful about extrapolation. So this is an example of that. The other thing we want to look at is, do you guys have any questions on this one? Let's get to question 4. So for question 4, we are told that a researcher is working with a model that uses the number of rings in an abalone shell to predict its age. He finds an observation that he believes has been miscalculated. After deleting this outlier, he redoes the calculation. And so the question is that does it appear that this outlier was exerting very much influence? So all they are trying to ask you is that, was the outlier influential? Remember, we did say that for us to get an influential point, if we omit it from the analysis, it means that what it changes the slope significantly to make a meaningful difference. So let's try to look at that. So before the outlier, we can see the R squared. Your focus should be mostly on the slope. And so here we can see the slope is the ranks here. And you can also see from the problem. Though you're also keeping an eye on the R squared too, but our focus should mainly be on the slope. So we can see this is with the outlier. That is why it is before. So we can see the intercept coefficient, the ranks too, and then the after. Now look at the slope. It's 0.32. After they remove that, it has changed significantly to what? 1.02, right? More than twice. Can you see that? And so we can see that then it means that what? The outlier is very influential. So you can see. So because this has changed significantly, we delete B and C because the no observation is not influential. It's not true because we can see when you look at this one here, the slope here is the what? Is the ranks. So we can see it has changed significantly from 0.32 to 1.02. So we delete B and C. We are left with A and then D. the observation was influential, which is very true for A and D. So we can see after it was removed, the slope of the regression line has changed by a large amount. After it was removed, the slope of the regression line has changed by a smaller amount. So we can see from here, there has changed by what, a large amount, because this is the slope 0.32 to 1.02, more than twice. I think almost even more, maybe close to 3 times or more than 3 times. You could just multiply this by 3 to see. So that is how to check for influential point. So we have this one here. Your main focus should be on the slope. Whilst we see, you can also see the R squared has also increased significantly. But we did say it's something we are keeping an eye on, but our focus should be on the slope. It is very important that you identify the slope. And you can see that in this problem here. It says that this is what he uses to predict. So he's trying to predict its age, and then he's using what the number of what ranks. So you can see that is the explanatory variable. Now let's get to 8. 8, we are told that suppose you fit a linear model to some data, and then let's look at the residuals here. For the residual shown, tell whether you would try a re-expression, and if so, why. When we look at this thing here, what do we need to look at? We are seeing that it's not bending or it's not curved. Remember when we talked about this in chapter 7, that so we can also see from here there are no outliers, and then you can also see they are evenly spaced. And so when we look at this, we would say that no expression is because this is the residual plot, which is what they are evenly spaced. So that is what we are interested in. We can also see there is no outliers, there is no pattern too. So those are some of the things you always need to look out for. To be able to understand this more, you could look at your chapter 7 homework when you were given some residuals. I think we did that in class, and then the assumptions they violated. You can see this is not violating any of them. The other one we want to look at is question 16. So for question 16, we are told that as scientist Robert Ball examined the relationship between the volume in which gas is contained and the pressure in its container. And then the scientists used a cylindrical container with a movable top that could be raised, blah, blah, blah. And then we are asked that find a suitable re-expression of pressure we should fit a linear model, and then check whether it's appropriate for modeling the relationship between pressure and then height. So let's look at what the first question is saying. Which graph below accurately represents the scatter plots and the regression line for the linear model of pressure versus height? So we just need to click on this data here, and then let's click on this one here, and let's click on open and start crunch. So you see, I have been able to open the data and start crunch here. And then we are looking at, so when you look at this one here, the Y is the pressure, the X is the height. It is the same for all of them. So we are the question is that which of them accurately represents the scatter plot and then regression line for the linear model. So let's try to do that. So to do that, we have the data here, and you know how I got to the data. So we go to start, we go to regression, simple linear. Our x, you can see from here, is height. So height. I am taking it from here. You can see the possible answers you have here is height. And it cuts across all of them. The y is the pressure. Okay. And then, so let's try to hit that. We do not care about this. Let's look at this one here. So it looks like this and then this way. So looking at all these, which of this best fit? Which of these ones look like this? We can see it's A. Can you all see that? Can you all see that? Okay. So you've been able to answer A. But then you can see there is a problem because when you look at this one, this is looking like a curve and not linear. But the R square, look at the, you see, we learned last time that look at the, you see, it's very high. But last time we talked about this already, so you shouldn't be surprised to see stuffs like this. And then now let's look at what B is saying. So it says that which could be a suitable re-expression. So remember last time in chapter 7, we looked at how to transform, so especially when you face situations like this. How do we transform this y variable to make it linear? And then I remember I produced a table of what to do. So when you look at this curve here, when we looked at how to transform, we didn't talk about any of these two. We talked about C and then D. But looking at what we have here, so if I were you and this is multiple choice and you are confused, you could try both of them and then you'd see. But for me, I know because this is like down and it opens here, I would use the 1 over y. You can see, you can find this in the chapter 7 notes. So to be able to do the let's transform, we just go to edit. And remember last time we talked about transforming the response. Transforming, our focus is to transform the response variable. That is what I taught in class. So we come here and then we have this one here. So in this situation, we have two, this one and that one. So let's try this one first. So 1 over pressure is same as the 1 over response. So if you click on that and you hit compute, you see it has transformed it nicely. Do you see? And so when you look at this C here shoots that. Any questions? Let's try to also see if let's try to do y squared 20, what happens? Just curious. Do you see? So you see, if you do y squared, it's even worse. So it is 1 over y. And so when you look at this one, this, so when I look at, I don't look at the numbers here. I rather look at the point and then the line. It looks perfectly increasing. Decreasing is out. You see, that's it. Even though it's not perfect. Now, when you look at this, you see yours is in like it's starting here. But look at this one here. Do you see that? Look at this is like from 0.01. But you see it's like here it's not perfect as this. But there is something you can be able to look at the difference perfectly what increasing because it looks like everything is on the line. Strong, very strong linear. And then look at this one. It's strong, but it's not what positive, it's negative. So this guy is out. Not so good. This is not so good. So you can see it's easier for you to see. It's C. So that is what I have for today. Let me see. Good. Good. How did I know it wanted the reciprocal graph? So I knew that I had to do some modification because we are told from here. And you could also see that if I try to make here none, we get this. And I knew from the problem here says that which could be a suitable re-expression, which means that you have to transform pressure. So it says which could be a suitable re-expression of pressure. So that means that I knew that because the question is asking me to what to transform. Now to transform, we had so many things in the we learned last time. But what do I need to do? So what I need to do, I knew this was out, this is also out because we are trying to transform the response. So this A and B is out. So these two were in contention. And I did tell you that even if you get to a point that you are confused, one of them will transform it better than the other. That is why you could try C, we tried C, and then we also tried D. If you try D, D is what pressure squared. You just need to come transform to y squared. And then when you look at that, just look at this. Too bad. So this is not good because we are trying to make it more linear. So then I knew D is out. Then we just did C, and then we saw that C was good. Yeah. So that is how I managed to know. And then now the question wants you to do, we did this, and then let's look at the R squared. This is very perfect. Let's look at the R squared, 0.9999, which is almost what 100%. So it's a suitable re-expression. So that is how to answer that. Um, I can do all your homework problems. So I think we've done about, let me see, one, two, three, four, five, six of them. So I believe you should be able to do the others. And make sure, I think chapter 7, the deadlines are approaching, so no, make sure that you do them. I'm coming to type the password for today's attendance in the chat box. So I have typed the password for today's attendance